Was he the good influence keeping us all on the clock? So, good morning. Today is semi-simplicial types, and I should emphasize that this, despite the normal dedication of this slot, this isn't a sort of research seminar kind of talk. This is expository, setting out a problem that various of us discussed quite a bit last term. A fair bit of this, I'll be recapping the talk that I gave near the beginning of last term, where I described the same problem, and I'll also recap a little bit some of the progress that was made last term on it. So, semi-simplicial types, I want to talk briefly about the second thing I'll do is talk about starting to attempt to define them. And the first thing I'll do is talk about the motivation. So I'll talk a bit about the motivation before specifically getting into what they are, because the motivation is kind of a very big picture that we won't actually reach any of at all in the actual concrete definition. And so the tricky bit when we get to it will be that for the definition, there are several different classical versions, and then when we try to take them to the type theory, some approaches kind of fall completely flat on their face, and other approaches seem promising, but still uncomfortably difficult. So there'll be a lot in this talk about things which don't quite work or seem to work but are hard to make talk. So it's a somewhat frustrating sort of a talk, but interesting, I think, and fun nonetheless. Both fun and frustrating, like any good problem that you haven't solved yet. So the motivation. Why do we care about semi-simplicial types? Why is this a good thing to think about? Well, simplicial sets, in a classical foundational setting, simplicial sets in a classical setting, simplicial sets are, well, certainly they're a very classical and very well understood setting for homotopy theory. They're kind of one of the best, most classical settings for it. And more recently, thanks to Vygotsky, they're a model for type theory with the univalence axiom, and more generally, just about anything else that we can reasonably call a homotopy type theory. For Vygotsky, this model is the kind of the genesis and justification for everything that deserves to be called a principle of homotopy type theory. It's homotopy type theory, or almost some days anything that deserves to be called type theory. It's a major justification for the new rules and so on in TS. So, but this model, whatever extent one may take it as a justification for type theoretic principles, it's a very nice and very important model of type theory. So, yep. And, yep. But not just any old model. Vygotsky does generally view this model as the central one of importance, just as classically the set model has, for some purposes, been viewed as the main motivating model. I think I'm not misrepresenting Vygotsky's views here. Is that safe to say? So in any case, it's an extremely fruitful model for type theory. And so if we want to various things internally to the type theory. So, there are several things we could try to do. Essentially, both of these we might want to do internally to the type theory. We might want to study homotopy theory internal to the type theory, but not in a sort of synthetic way, not in the kind of way of simply using types of spaces, but simply an internalization of the classical theory, simply to try and give a fully constructive, fully type theoretic treatment of the classical approach to homotopy theory using simplicial sets. So we could want to internalize that. And also, of course, we can want to internalize parts of the construction of the models of the type theory to get, for instance, relative consistency results, that we can say we can take any model of type theory without univalence and look at simplicial types in it to get a model with univalence, or something along those lines. And I know Thierry and I think Steve and who else has been, but yes, a few people here have been working on that to some extent. There are a lot of very good reasons for wanting to internalize some of the classical theory of simplicial sets. And also I've said simplicial so far, but much of this goes to a lesser extent for these slightly different things called semi-simplicial sets, which are in some ways certainly not quite as nicely well behaved as simplicial sets. Certainly their theory is far less well developed than that of simplicial sets themselves. Simplicial sets, we know just about everything we might want to know about them. That's not at all true. But we know as much about simplicial sets as we do about just about any other model for homotopy theory or anything similar. Semi-simplicial sets we know much less about, and it certainly doesn't develop quite so smoothly. But at the same time, it seems hopeful that one could develop analogous parts of the theory in semi-simplicial sets. It seems an interesting and comparatively unexplored classical area. So for internalizing them, how might we go about it? Well, we'd start by simply writing down the classical definition and then writing that down in type theory, right? That shouldn't be hard. So what are the classical definitions? Yeah, absolutely.
Often in type theory, we run into coherence problems, like the kind of the data lemma that coming up in the work I did about data. And these naturally give rise to a kind of simplicial structure of coherence issues.
Yes.
And for that too, I think we want to have this notion of a simplicial type and then contribution on substance.
Yes, these give a very good framework for setting up and giving machinery to handle coherence problems insofar as they give, among other things, that can be seen as a model for infinity one categories, or restricted classes can be. And if that was mostly gobbledygook, I will be giving a digression about halfway through the talk, which will make it less gobbledygook and go into more about what we mean by coherence problems and so on. So the classical definitions firstly, there is a combinatorial definition classically, which I won't mention at all, using lots of funny identities, and it's reasonable, but it doesn't become particularly fruitful because it can be written much more cleanly, classically, in terms of functors. So you define bold-faced delta, the simplicial category, is defined as the category of finite non-empty partially ordered sets. Sorry, not partially ordered, totally ordered. Finite non-empty, totally ordered sets, and of course the monotone maps between them. So that's a straightforward enough category to say what it is. Let's briefly, for a moment, give some notation for it as well. We write n for the finite non-empty totally ordered set that begins at 0 and goes up to n for n any natural number. And obviously this is always a finite non-empty totally ordered set. So this gives us good concise notation for the elements of this category. Obviously not every element is of this form, but up to isomorphism it is. So these give, we can use these if we want to take a small skeleton of that category. And we often consider the category as essentially given by that skeleton. And then it has a close cousin, the subcategory delta I, the semi-simplicial category, which consists of the subcategory of delta with just the injective maps. And this now allows us to give a very quick and clean definition. A simplicial set, or a semi-simplicial set, is a functor from the simplicial category into sets, or of course, respectively, the semi-simplicial category. So this is absolutely. Yep. So I know. So I will be looking in just a moment at concretely what these functors end up looking like and why they are a homotopy theoretic notion. So I'll come in a moment to specifically looking at what the maps look like. But absolutely, as you say, one of the things that one gets in this definition is that all the maps go upwards, because downwards you can't have a map from an injective map from a bigger finite set to a smaller. So yes, so concretely unwinding what these look like. Yep. Thank you. Absolutely, yes. Thank you very much. Crucial ops. So, if we've got a simplicial or semi-simplicial set, what does it look like, and why is it reasonable to think of it as some kind of space, some kind of geometric or topological object? So firstly, let's look at a simplicial set first. Is, let's call it X. We don't need to know what it does on every random partially ordered set that you write down in the morning. We've got a skeleton of the category, and so we just need to check what it looks like on those. That's determined by the sets. So by its action on the objects n and the maps between these. So in particular, we tend to simply write x sub n for the action of x as a functor on that particular set, and we typically think of x as given on objects by just this sequence of sets x sub n. And so we have, well, let's just So this is a set. So X itself is a functor from the simplicial category to sets, and so here we're applying it to a particular object of the simplicial category, so we get a set. So looking at just the first few dimensions, we have few sets like this, and what maps between them do we have? Well, they're going to correspond in the opposite direction to maps between the appropriate orders. So we've got 0, 0, 1, 0, 1, 2, and so on. And what maps are there between these? So there's the map from, looking between these two, there's a map from 0 to 1, which takes 0 to 1. So there's a map from 0 to 1, which takes 0 to 0. And then there's the map from going the other way, which sends both 0 and 1 to 0. So for reasons which will become possibly not apparent, we call this one delta naught and this one delta 1. So that these are the maps going up like this are the so-called face maps. And the reason why the one that goes to 1 is called naught and the one that goes to naught is called 1, which seems crazy at this level, becomes more reasonable further up, where the crucial thing is not that its image consists of one point, but that its co-image consists of one point. It's missing out one point, and so we name it for the point that it misses. So these are delta naught and delta 1, and then this we call sigma naught going the other way, for reasons which again will become reasonably apparent. So this now gives us functions that going the opposite ways here, which again we call, usually we change from Greek to Latin and call these d naught, d1, and s naught. Which, sorry? Yes, exactly, because of the that they go, the functions we have go in the opposite direction. Yeah, from those arrows there. And so what should we interpret this as? This allows us to think of the first two dimensions as looking like a reflexive graph that we have. So from these arrows we can see x naught as points or vertices, and x1 as arrows, so we could have x and y in x naught and f in x1, and we write this to mean that the zeroth face of f is y, and the first face of f is x, again with the indices the opposite way around from what one expects in low dimensions. But the two faces, so the two faces of this one cell are these zero cells x and y. And what's the S naught going the other way? It's like the reflexivity map in a reflexive graph, or the identity map in a category. It gives us, for any, I should say, this is, so these are the two faces of f, and then for any x, we have the degeneracy on it, the S naught of x, is something which, when we look at how the maps compose in the category, the two faces of it both end up being x itself, just because when we go up and back down again, either way we get the identity map here. And so this gives, for every object, an arrow from that object to itself. So we've got the start of a geometric picture here. What happens happens when we move up to 2 dimensions? Well, we've not got enough space now, obviously, to write up all the maps, but we in that much detail. But we can indicate some of the key ones again. That again we have injections from here to here which miss out any one of these. We also have, by composing from here to here, we have 3 maps from x0 into x2 that pick out any one of the 3 points. Between those again give us face maps, like the Ds, and between them they let us get x2 as triangles. So we can have alpha, if we've got any alpha in x2, it's got the 3 maps from there up to there give us 3 points, which let's call them x, y, and z. The 3 injections from here to here give us 3 arrows, which we'll call them f, g, and h. When you look at how those maps commute, they show that these things fit together like the boundary of a triangle, and all in all, we get that. And the degeneracy maps, again, give us the maps going in the other direction, give us, from lower dimensional things, we get partially degenerate higher dimensional things. Yes, so I've been kind of introducing these 2 bits of terminology by stealth without saying in general what they are. So face maps and degeneracy maps are the 2 important classes. So the face maps were they're the functions in a simplicial set arising from the injections in delta. And so, for instance, as we saw, the maps which from this triangle gave us f, g, h, and x, y, and z, all those came from the injections going from these lower dimensional places up to higher dimensional places. And so from a higher dimensional thing, they give you a lower dimensional part. And the degeneracies are the ones that are orthogonal to that. They're the surjections. So again, consider this bracketed part repeated. From the surjections in delta. And if we were getting one of these from a topological space, which is a very standard construction, which I won't go into the details of for anyone not familiar, but we do it in exactly the way these pictures suggest. Then the degenerate ones amount to the ones which are constant in some sense in some dimension. So, for instance, this would the reflexivity from any arrow from any point to itself is simply implemented as the path, the constant path at that point, where at that point you just sit there for a while. So so we have the face maps and degeneracy maps, and it's yes. Yeah, exactly. And so these were the Ds and the S's in the presentation over there, or the deltas and sigmas on the Greek side. And the fact which is going to come back and be of interesting relevance later, which is that every map in delta factors uniquely as a surjection followed by an injection. And from this, it follows that to know all the maps in a simplicial set, to know all the functorial action of it, you only need to know the part of it given by the degeneracy and face maps. So the degeneracy and face maps of a simplicial set completely determine its functorial action. So just as we only needed to know this single sequence of sets xn, we now, if we know those plus its face and degeneracy maps, then we can completely recover the full simplicial set as a large functor. So that's a simplicial set. And what's a semi-simplicial set? It's exactly the same, only it doesn't have the surjections in the domain category. And so under this correspondence, that's exactly saying that it doesn't have the degeneracy maps. So no, I meant to write semi there. So it's just like a simplicial set without the degeneracies. Not quite the same as that, since the face maps don't have to be and generally won't be injections. It's simply that the injections in the domain category correspond to the face maps in the simplicial set. So we have face maps, and they can be arbitrary, but we just don't have any degeneracy structure on it anymore. And so we can draw exactly the same pictures like this. We can just no longer draw pictures like this. And that slightly misleadingly oversimplifies the relationship between them because it pushes on towards thinking of them as really looking very nearly exactly the same. And it slightly sweeps under the rug the extent to which they end up behaving, in some ways at least, fairly differently. But it's not. So they look exactly the same, only beware they behave more differently than one might at first expect. So this gives us, classically, two nice, very clean. They took one fairly sparsely written blackboard to define classical definitions of simplicial sets. What goes wrong if we try to replicate this definition in type theory? The first thing that goes wrong is that I need a new piece of chalk. Sorry? Yes, but I want that one at the top. I guess I could throw this down the bottom, but I don't think I need anything on this bottom. So So in type theory, how does this turn out? So the first thing is, can we define delta and delta I? How does that go? It goes absolutely fine. There are some significant subtleties in the definition, and some very big subtleties indeed, in the general definition of a category internal to the type theory. Those who were here last term and were at Mike Schulman's talk will have heard quite a bit about that already. But again, there are coherence issues, which I won't get into now for this part. So for a general category, there are great subtleties, but in this case, since these are categories that are made up out of entirely combinatorial objects that are just H sets, it's absolutely fine, and all those subtleties trivialize down, and everything's okay. So these are just H-set categories. So in a more traditional language, that's because all of their Hom sets are objects that satisfy uniqueness of independence proofs. If we have, we can see by looking at any two of these can be simply defined as certain finite sets. The exponential between any two finite sets, I should say I'm assuming functional extensionality. The exponential between any two finite sets is simply another finite set of the appropriate size, and that's type theoretically easy enough to prove with functional extensionality. And so from that, it follows that the Hom sets of this are finite sets with decidable equality. So So general categories are hard to define, but H-set categories are fine. So it does matter. Type theory, I'll just give a brief one-liner now and then, yes, another time to discuss this more would be great. So type theoretically, an H-set is a type which satisfies uniqueness of independence proofs internally. So any two objects are equal in at most one way. And homotopy theoretically, that corresponds to an essentially discrete space. So a space which is homotopically equivalent simply to a discrete space. So something which has no kind of loops or higher interesting information in it. So, yeah. So defining these categories, no problems. But defining functors into type, this is where the problems come up. So let's give a bad definition for a moment. I'll come back to that in a moment. And the quick answer is, yep, that works very nicely. At the same time, that's not all we want. We're greedy. We want functors into general type. So functors into H-set is something, and it's nice, but it's a restricted case. So, yeah. But yes, I'll come back to that in a moment. So the bad definition would be a functor x from delta to type, and I'm regarding this as not kind of an instance of the general definition of functor with these being categories, but simply a kind of, if we beta reduced that and said what is a presheaf on this category in its own right, this definition I'm going to give is not one to leave this room. It's a wrong definition, but it's a very tempting wrong definition, so it's one worth looking at. No, just wipe it afterwards. Bleep out the appropriate bit. So the presheaf is going to start with a map on writing in some bastardized version of record syntax. So yes, it matters. I think I forgot to pick up my ops when I left the house this morning. Yep, it absolutely should still be op. So first we want its action on objects, which is a map from the objects of delta to type. For each of these finite number totally ordered sets, or just for each natural number, we want a type. Great. Then for then we want an action on arrows, saying that for all m and n in the objects of delta, and for every function from m to n, we want a map from objects of x at m to the other way around. I'm really sorry. I'm in a very covariant mood today. So we have the maps, and then we want functoriality. So functoriality, what does that mean? That just means we want that x respects identities, so that's for all m. We want to know that the arrows of x applied to the identity on m equals the identity on the appropriate set. And then x respects composition, something similar, which I won't write out the details of. So that looks very temptingly like that's a reasonable definition of a presheaf on delta. What's wrong with it? The trouble is that we've got things which are specifying equalities now without specifying any relationships between these equalities, but there are relationships between these equalities which should hold. So it's propositional equality. I'm trying to avoid the words intentional, extensional, because they get used different ways around by different at different points. So
This is the first lecture.
Yep.
Sure, maybe give us a brief glossary there of terminology. So equality, we mean type, the identity type.
Yep. By propositional equality, the identity type. By definitional equality, we mean the judgment of equality within the theory. And intentional and extensional equality can mean either. Different people have used them different ways around, so I'm not going to use those words at all as far as I can avoid them. And I mean, it's for reasonable historical reasons that I've ended up having both meanings, but it ends up horribly ambiguous. So. So we have the face maps simply by here. So I'm not sure, what do you mean by respecting face maps? Yep. Yep. This is the. So the problem with this is that it's missing coherence equalities. In that, for instance, in this category, we can prove associativity, and that's some equality within the category. In type, again, we can prove associativity of functions. And then we can chase that through here and get a complicated diagram where one goes, has two natural things in the functor and gets one path using reassociating and the respecting composition one way around, reassociating in one category. Or one can use respecting composition and then reassociate in the other category. And those give the same thing. And we should have an equality in here that says that they give the same thing. And if we don't include that in the definition here, then this can allow diagrams where they don't give the same thing. This is, I'm always aware when I try to give a quick description of coherence problems, I'm sort of selling it badly, inevitably, because, well, why do you need the higher coherence equalities? What's wrong with leaving them out? And it's hard to give a concise example of why you need them. Do you have a concise example? Absolutely. No. So yes. So if we were wanting to go in and look at an example of how incoherent examples can arise, then the groupoid model gives probably the nicest way to write down a very concrete example of how an incoherent functor can arise. So for the absolutely. So yes, in the groupoid model, that would be how this interprets, where these become natural isomorphisms in the groupoids.
And then when you have 3 arrows in a row,
yep.
you make 2 triangles like this, you have an isomorphism here, and another isomorphism here.
Yep.
And then you have the posits of isomorphism, and there will be no relation between those isomorphisms.
Yes. Yep. So there are 2 ways to show that x of, so writing some of these things as coercions now, that x of f composed G composed H is equal to x of f composed G composed H. Why is it a bad thing? On the one hand, I'll say, take my word for it, when you get onto working with these, if you try and use the incoherent definition, sooner or later, about a couple of weeks in, you'll find that you need this. But a possibly better answer is, well, by analogy. So here, we've not given anything higher than the equalities at first level. If we're thinking just propositionally, just in terms of propositions where we didn't care about equality of elements and had stopped before giving equality at the 0th level, so say we'd stopped there, it's reasonably clear to see now that that would be perfectly adequate if we were working with functors into things that we just think of as propositions, but inadequate because it doesn't include the commutativity as soon as we move to wanting to think about equality of elements. And it's for essentially analogous reasons one level up that stopping here is inadequate as soon as we have things that are more than H sets, as soon as we have things where we care about equality between equalities. So one level down, it's very clear to see why it's inadequate, because we're used to working with H sets a lot. At this level, one bumps into the inadequacies later, but they're still there. So this is unfortunate. This means that if we simply write down the set theoretic definition of a pre-sheaf on delta, that doesn't give us what we need.
There are 2 ways to show that.
So we should. So there's nothing specific about the 2. The problem is, or multiple really would be a better way to say things here. There should be, or potentially multiple ways to show this, and in a well-behaved pre-sheaf, all the different ways to get from here to here should be the same. But if we just give this definition, that doesn't force them to be the same. So the 2 ways are, we can either show in this category that these 2 things are equal, and then apply x, or we can use the functoriality of x to pull these out into functions, and then we can use the fact that associativity of functions holds. And that all of these correspond to things in higher category theory as well. Again, that's where I'm afraid I can't give a quick example of why you run into something, but when you try to develop the theory of these, a week or two in, you will hit a point where you need something like this. And it's the analogy of one level up of why we need the commutativity here. The commutativity here can be seen as that there are, if you have a pair f and g, there are multiple ways to get from x at here to x of here, and the respective composition tells you that those two ways are the same, or that any of those multiple ways are the same. And this is exactly the same sort of condition one level up. So why not just add these? Not surprisingly, the trouble with just adding these is that, well, you also need coherence conditions at the next level up, and the next level up, and so on. And for the coherence conditions, they proliferate, and even classically, they quickly become combinatorially extraordinarily difficult to handle. So even in a completely classical foundation, there are ways to handle infinite coherence conditions, but they involve a lot of very heavy machinery, which itself is much harder to develop and involves, and if we tried to do that in type theory, we'd run into the coherence problems even in setting up that machinery. So this approach seems close to hopeless for the type theory. I've not seen anyone give a formal statement along the lines of that this couldn't be made to work, but I don't know anyone who's trying to make this work for general types, and I can't see how you would. So type valued yes, yeah. Several very intelligent people who worked very hard on it and didn't succeed. So, close to a proof.
So the fact that you worked hard on it, that's almost a
Yes.
okay. Not a
So, it's worth mentioning as a side note that, as Egbert said, that's only because we were kind of being ambitious here and wanting fully type-valued presheaves. If we wanted H-set valued presheaves, then that's perfectly fine. So why is it fine? Because this condition, when we look at it, it's asking for an equality between equalities, and if everything in sight is an H-set, then equalities between equalities come for free by the H-set assumption. And in fact, so generally, if we have any fixed finite H level, I don't want to say it's fine, but it's doable. In principle, because one can just write down the coherence conditions up to that finite level and then stop there. So certainly the level above H sets, which is H level 3, I think, I can never remember the indexing. So H level 3 or so, we can simply write down this and a few more coherence conditions that are familiar from higher category theory, and that works. And as far as that one can write them down classically, one can then do them. One can do presheaves at that finite H level. So
you mean more that the simple matter of associating
precisely, yes. It's straightforward in principle. The calculations are intractable, or after medium n. So these are fine, and developing the theory of these seems like it should be great. On the other hand, let's for now keep being greedy and ambitious and wanting fully type-valued ones of these to see if we can do it. So we can say here the functor approach ran into horrible problems. Let's go back to the drawing board. Is there another way we can do it? And we can get a way which actually maybe even seems type theoretically more natural from the start. So that sounds plausible to me, but I think you and Thierry know whether it's better than I do. So H set, simplicial H sets do seem like they could reasonably suffice for a lot of important applications. They're certainly not kind of a boring trivial case or anything like that. So, yeah. So if we go back to the drawing board and think very concretely and start, as ever, by kind of looking at a trivial simplification. If we just look at the first few dimensions, we said dimensions 0 and 1 were for semi-simplicial sets, they were just a graph in the category theorist sense. For simplicial sets, that was a reflexive graph in the lowest dimensions. And if I asked you to write down in type theory the definition of a reflexive graph, let's say, or a graph, you might say it's two types, x1 and x0, and maps source and target between them, and maybe a reflexivity map going up. Or more naturally, I think you might also say, it would depend on your taste, which you said first, I guess. So typically, in type theory, a graph might be there's a type of objects, and then we could say there's a type of all the arrows and maps back, or the other way, we could say it's got arrows, which is simply a map from pairs of objects into type. For every pair of objects, we have a type of arrows between them. And so we're not looking at all the arrows as a single type, but making them dependent on their source and target. So arrows are dependent on their source and target. And this gives us dimensions 0 and 1 of a semi-simplicial set. We could absolutely also say that. Yes, it is. If I'm... Yes. There's no problem in principle in the fact that they're isomorphic, but very often the uncurried version is the more convenient one to work with. So when thinking from a kind of programming point of view, this version of the isomorphism where essentially whenever one homs out of a limit or an inductive kind of type, when one then pushes through that isomorphism to get an iterated hom, it works out much more cleanly for kind of computational purposes. So certainly these are provably isomorphic in type theory. There's no in principle problem. Yes.
Culture clash.
Yeah. Yes. So. It's a good. Yes. Yes. Yep. Yep. Sure. So we can extend this idea to semi-simplicial sets. It's we have x0 is a type. The one cells, like the arrows of the graph, are dependent on pairs of objects. That, and again, we could see this as a product. The two cells are dependent on configurations of 0 and 1 cells that look like the boundary there. So this is saying for every x, y, z from x0, and if you have an arrow from x to y, and an arrow from y to z, and an arrow from x to z, then we get a type of triangles filling that boundary, and so on. And that's an extremely slippery and so on, which I'll come back to in a minute. But an extremely slippery and so on. So this ... is harder than one expects it to be. But let's contemplate it for a moment in low dimensions. At least up to any finite dimension, this gives something which classically, or actually, no, I mean, if we do this classically, we can write this down without trouble in all dimensions, and it gives something which is completely equivalent to the notion of semi-simplicial set as defined via a functor. So yes. Yep. Yep. Exactly. So so classically this is equivalent. So classically the ... isn't hard to fill in, and this is equivalent to semi-simplicial sets presented as functors. We're just looking at it a different way, where we say we're just considering the xn as dependent over the type of n cells as dependent over what we can call the set of n boundaries, which is defined as a certain limit of the earlier xn. So if we're looking at it, or earlier xi, I should say. So if we did something analogous to the product there, we could pull all of these bits into a single limit type of triples of arrows and triples of objects that were connected appropriately. And this is something which is absolutely, again, familiar from homotopy theory. This is what's called Reedy diagrams in homotopy theory. So this is known as yes, Reedy, yep, it's somebody's name. So let's see, given the time, I won't give the general definition of Reedy diagrams, but a definition that covers a special case that we're working in. So an inverse category is a category in which the relation where A is less than B if so this is a relation on objects of the category where A is less than B if there's a non-identity arrow from A to B. So this, so it's a category where this relation is well-founded. So it's saying from every object you can kind of go down along the non-identity morphisms, and you have to bottom out somewhere. And so if we look at the simplicial and semi-simplicial categories, the simplicial category is not one of these. We can use the degeneracy maps to go to travel back up along the degeneracy maps the whole way up to infinity and never stop. But in delta I, with just the injections, if you're traveling back along non-identity morphisms, then you're always going downwards, and so sooner or later you hit 0 and have to stop. So and so generally, so the advantage of inverse categories is that in any category with a notion of fibration, so in other words, a subcategory, a subclass of the morphisms of C, so with no conditions at all for the moment, and I'll put conditions on it in a moment. Define that a functor from an inverse category I into C is Reedy. Sorry, yes, bless you. So a diagram over the inverse category in C is Reedy, and this is generalizing the idea that we have here that the type of n cells was dependent over their n boundaries. In a Reedy category, each object, we look at the things that were below it in that ordering as its boundaries that it should be dependent over. So for each B and I, the map from xb to the limit over so we have to be a little careful here. We want the limit over the maps f from A to B where f is a non-identity, the limit over that restricted comma category of xa if this limit is a fibration, and that's exactly generalizing the condition above when we take this in the case where I is simplicial sets. When I certainly, yes, more often Reedy fibrant, absolutely. I've come across some places that just call it Reedy, but maybe I should better call it Reedy fibrant. Now, this notion, what do we need for this to be reasonably well behaved? Aside from anything else, what about these limits existing? We didn't put any assumptions on C. So to interpret this definition in full generality, we should say if it's Reedy fibrant, if these limits exist, and then these maps are fibrations. But thank you so much. Yes, I don't know why I am refusing to accept contravariance today. So this notion turns out to be reasonably well behaved and in particular the limits always exist if under fairly weak assumptions on C. So as long as C has that fibrations are closed under identities and composition and under pullbacks, and as long as so those together with I being slice finite, that any slice is essentially finite. There are various ways of putting this, but so I has essentially finite slices. If you look at any object, essentially enough that the category you're taking, the limit over here, is essentially finite. Absolutely, yes. So, yeah. So, yes, in many areas of mathematics, this would be more familiar as stable under base change. So under exactly, yep. Yes. So this ensures that under a quite weak set of conditions, these are well behaved. In particular, if we have a type theory and we look at it externally, so we're here, we're not working within a type theory, we're being logicians and looking at a type theory from some meta language outside it. And so if we have a type theory, then the classifying category of T, so the category of type of contexts of T and context maps between them with dependency, the dependent types and contexts as the fibrations. So this is a Gambino-Garner weak factorization system on the type theory. This satisfies those conditions. And in that case, when we take Reedy's semi-simplicial objects sorry, yes, I want to say just dependent types, not contexts for now. No, I'm going to say context for now. I've slightly conflated two different versions of the approach. But then Reedy's semi-simplicial objects in CT look like the external interpretation of the sequence we wrote above. So they come out as contexts, not types, if we used this approach. So it comes out as not absolutely exactly that, but that with context instead of single types. One can get it to be single types by taking only dependent single types as the fibrations. Then one loses the closure under composition, and one has to work a bit harder for this, but one can still make something along these lines work. So this describes that nicer type theoretic definition as something familiar from homotopy theory, and gives a reassurance at some level that it's not that we haven't actually forgotten some more coherence conditions that should be in there. For the semi-simplicial sets, at least now, this does give externally a reasonable definition of semi-simplicial types. Can we do the same thing with simplicial types? It's
Yep. From bad definition to good definition.
Yeah.
The essential step there was solving the coherence problem. The way that you solved it was using this type dependency to force equations.
Absolutely, yes, thank you. That's an excellent point that I was forgetting to say. That the key thing here is that in the functorial definition, we had to assert propositional equalities for all the functorial action, and then we would need coherence between those. But here, the map, say, from 2-cell to any of its faces comes simply out of this type dependency. And so then the equations between these, that if I pass from a triangle to a side and then to a point, or to a different side and then to the same corner, those are both coming just out of type dependency, and so the equations between them hold definitionally. Absolutely. Thank you. Yes, that's a key way to look at how we've essentially solved the coherence issue by passing to this. So this gives us So the good definition which we can make externally is that a semi-simplicial type is a Reedy fibrant diagram on delta I in the classifying category of the theory. And this, and so I'll come a moment to internalizing it after just saying, why can't we take a similar approach to simplicial sets? Well, okay, we can't do this literally because delta isn't an inverse category. If you're familiar with the homotopy theory, though, you'll be saying, but we can still define Reedy fibrant diagrams over it because it's an instance of a slightly more subtle definition called a Reedy category, which is not surprisingly what Reedy fibrancy was originally defined for. And one can still define Reedy fibrant diagrams for a general Reedy category. However, in a general Reedy category, the limits that one takes here are not quite so simple. And in particular, they're complicated to the extent that the assumptions on C that we would need to be able to make those limits don't hold in the type theory. So to be able to work well with Reedy fibrant simplicial diagrams, we would need to be able to take limits in the type theory involving definitional equalities. And we know we can't do that. So I mean that in the meta language, if we're working with a meta language, we can write down this definition. But at the moment, and I'll come more to this in just a moment, we can't write down a single definition in the type theory which corresponds to this. So for any finite dimension, though, we absolutely can write it down in the type theory. So if we cut off this ... after, say, level 2, we can certainly write down a record type that is what I had there. So for any finite n, we can write the definition of Reedy fibrant semi-simplicial sets, or semi-simplicial types up to level n in the type theory as a single definition. Yeah. Absolutely. Why can't we do this by induction on n? It's I don't know about impredicativity, but yes. So this is really where the part where I'm saying here's what we know how to do stops, and the part where I say here's what we don't know how to do begins. It really, really, really looks like we should just be able to say, so we should be able to write down in type theory this definition by induction for all n. But several of us here, certainly I have tried, I think Thierry has tried, Hugo Herbelin has worked on it quite a bit, and has probably got the furthest of any of us, at least as of the end of last term, have tried. It's remarkably hard because most of the ways that one tries to write down the induction end up coming back to something like defining the earlier objects as diagrams via some kind of functor on some truncated version of the category delta I, and then to get the required relations between those diagrams to inductively build up, you end up needing coherence conditions, essentially. So